So let me preface kind of what this unit is about. We're in our last unit. And we'll have essentially 3 weeks of this. This last unit is kind of a bunch of different like little things that aren't necessarily super duper connected. Some of them are, some of them aren't. But it doesn't feel that way, I'll put it that way. All right, so it'll feel like there's a lot of sort of a grab bag of topics, in other words. So there's some changing of coordinate systems, there's some vector stuff, some matrix stuff, and then some parametric, not parametric, excuse me, polar coordinates and conic sections and things like that. All right, so yeah, so it'll feel a little bit like a grab bag of stuff, but it's not too awful crazy. All right, so I will get started, and we're going to combine two sections because those two sections both are polar coordinate sections. One's like graphing with polar coordinates, and the other's doing other stuff with polar coordinates. So it's like graphs and computing with polar coordinates. Okay. So here's what we're going to do. Usually, we use rectangular coordinates. These are the ones that we all know. The x comma y, where x is the distance from the origin left or right. And y is the up-down distance. Again, this is from the origin. So that's what we call the rectangular coordinate system. This is the one that we always been using. We're going to switch that out in 8.3 and 8.4 for polar coordinates. So before I talk about polar coordinates, because we're going to talk about polar coordinates today in 8.3 and 8.4, but we're also going to talk about parametric stuff in 8.6 and 8.7. All right. And that's another coordinate system. That's another way to do things. The reason why we would maybe want different coordinate systems is because that some things are easier to do in polar and some things are going to be easier to do in rectangular, right? There's just tasks in polar that are much easier, and there's tasks that are in rectangular that are much easier. So the reason why you want another coordinate system aside from the rectangular is that, again, sometimes things in polar are much, much easier to deal with. Okay. So that's why we're going to do that. So we will also use polar coordinates. And the polar coordinates are, for any point, are r comma theta. R is the distance from the origin. And our theta is the angle from what's called the polar axis, but we always think of it as the x-axis. So let me kind of draw a picture of what's going on. So let's say we have this point out here. In our normal rectangular coordinate system, we'd start at the origin, measure out x units, and measure up y units. And so the rectangular point would be x comma y. By the way, the reason why we call that the rectangular coordinate system, or sometimes just the normal Cartesian coordinate system, is because you travel along rectangular routes. Does that make sense? Straight left and right, straight up and down. So you can travel along rectangular routes. Now we're going to deal with a polar coordinate system. And the polar coordinate system says, well, what angle would I have to travel from the origin to get to my point? Oops. That angle is our theta. And the distance that we have to travel is the distance of this line, which is the r. So r theta is the polar coordinate of that point. Okay, so this is the big picture. By the way, I drew this in the first quadrant. Obviously, if we draw the same type of picture in the second quadrant or the third quadrant or the fourth quadrant, it would be the same. Let's say we drew this in the second quadrant. We have an x, a y. Be careful, the theta will actually be that one. Okay, when we say angle from the x-axis, we're talking about the x-axis, the positive ray going out of the origin. Does that make sense? So that's the polar axis, or the x-axis. So this is the polar axis or the x-axis. X-axis in rectangular, polar axis in polar. Sorry. That makes sense? By the way, if you think about it, if you use this theta and then you add 2 pi to it, you're back to the exact same point, right? So using that theta and then adding 2 pi, adding 2 pi again, that actually gives me infinitely many polar coordinates, points that land at the same spot. Because you can just go around and around and around. And so oftentimes people will, just as we always do, specify that the angle has to be between 0 and 2 pi, or between negative pi and pi, or something like that. So they'll say, well, only use angles between 0 and 2 pi, or only use angles between negative pi and positive pi, so those types of things. All right. So I wanted to at least bring your attention to that, what angle we're talking about, and then there. Now, the big thing about polar coordinates, well, there's two big things. One is the conversion between polar and rectangular. And the other is, how are we going to graph equations in polar? What do they look like? What do they look like compared to rectangular equations? So the big things are conversions and graphing in polar. Right? Let me start with the conversions. From polar to rectangular, and obviously the other way too. Okay. I like to use this picture because it's the one in the first quarter, the one in the first quadrant gives you the easiest feel for it. Note that this picture here is just a picture of a right triangle. So if you go back to all of our identities about the right triangles, we essentially have all of the conversions, okay? Now, I'm gonna write the conversions down, and then I'll kind of explain where each of those comes from. All right. So the first one is going to be r squared is equal to x squared plus y squared. I'll write all 4 of them down here before I move on. The second conversion equation is going to be x is equal to, r times cosine of theta. The third one is going to be y equals r times sine of theta. And the last one is going to be tangent of theta is equal to y over x. So here's the deal. If you have r and theta, so if you know your polar coordinates, you can get your x and your y using these middle two. Right? So you can go from polar to rectangular using those. If you have your x and y, then you can find your r using this equation very quickly. And you can find your theta using this equation very quickly, using inverse tan, obviously. There's a reason why this is traditionally written this way, and we'll go through that once we get to what's happening. Okay. So these are the four equations for our conversions between polar and rectangular. And where they actually come from is something we've seen over and over again. The Pythagorean theorem and SOHCAHTOA. Hopefully it's pretty obvious that that first equation, r squared is x squared plus y squared, is just the Pythagorean theorem with x and y as the legs of the right triangle and r as the hypotenuse. So r squared equals x squared plus y squared is the Pythagorean theorem. R to the hypotenuse. SOHCAHTOA gives the others. The SOH means the sine of an angle in a right triangle is the opposite over the hypotenuse. So it's y over r. And then if you multiply both sides by r, you get r sine theta is equal to y, or y equals r cosine theta. Similarly, cosine of theta is adjacent over hypotenuse. The adjacent is x, the hypotenuse is r. You multiply both sides by r, that's what you get. And the last equation is just the TOA part, right? Tangent of the angle is opposite over adjacent, y over x. So these four conversions, these are the things you need to know. These are the things you need to, at least have written down, because these are the ones you're going to use. But they just come from Pythagorean theorem and SOHCAHTOA. Now let's use those to convert. This is going to be like the first thing we do. Use equations to convert. And we're going to start with polar and give the rectangular. Are we okay with that? So we're gonna take r theta and we're gonna produce an x comma y. All right, so let's say our polar is 3 comma pi over 3. As a rectangular, this is r theta. So I know my x value is going to be r times cosine theta. That is 3 times cosine of pi over 3, comma. And then my y value is going to be 3 times sine of pi over 3. All right. We could go to Desmos or use your calculator. I'll use my calculator a lot. But if you just take 3 times cosine of pi over 3, you get 1.5. And then 3 times sine of pi over 3 is, oops, you guys can read that here. Oh, yeah, good. It's about 2.60. All right. Notice I'm dealing with radians. So make sure your calculator is set in radians when you're doing this polar stuff. Oh, I should have maybe said this. I'm using rounded answers here. Obviously, if you knew that the cosine of pi over 3 was a half, you could use the exact answer. And if you knew the sine of pi over 3 was root 3 over 2, you could use the exact answer. So if you wanted to do exact answers, you could do 3 halves, comma, 3 root 3 over 2 as the exact answer if you like. Okay. I'm not going to ask for the exact answer. I usually ask for rounded to a couple decimal places. But if you know the unit circle well, you could give exact answers too. That makes sense? So I want you to take a minute, excuse me, and do a couple more. Take 5, comma, 3 pi over 4. And then take 3, comma, pi over 2. And let's take -4, comma, pi over 5. And convert all of those from polar to rectangle. Alright, going from polar to rectangular should be pretty straightforward every time. I hope. Every time the x value is going to be r times cosine of theta, and the y value is going to be y equals r times sine theta. So for 5, 3 pi over 4, I just have to plug that in. 5 cosine 3 pi over 4. I get about negative 3.54. If the decimals there. And then I get a positive 3.54 as my y value. If you're looking to do the exact answer, 3 pi over 4 gives you negative root 2 over 2, comma, positive root 2 over 2 when you do cosine and sine. So just multiply those by 5. So as an exact answer, this is 5. This is 5 times root 2 over 2. And this is just 5 times negative root 2 over 2. One exact answer. And that should make sense in terms of getting a negative for the first coordinate and a positive for the second, because we're at angle 3 pi over 4, so we're shooting off into the second quadrant. Does that make sense? So that's going to have a negative x value, positive y value. Just like when I dealt with 3 comma pi over 3, I was shooting off into the first quadrant. So I should get positive, positive, which I did. Now 3 comma pi over 2. Well, I don't even put it, I can put exact on this one. You get 0 comma 3. Hopefully that makes sense. Pi over 2 is shooting straight up what we normally call the y-axis. With polar coordinates, the y-axis is called the line theta equals pi over 2. Okay. That's the line in. So the theta equals pi over 2 line. And if we're moving up 3 units along that, we're just getting to a point 0 comma 3 up here, right? Moving 3 units up along that line. Now the next point in polar was negative 4 comma pi over 5. Now pi over 5 is a angle that shoots us off into the first quarter, or first, I keep saying quarter, first quadrant, excuse me. So it's shooting us off into the first quadrant. If I put a negative 4 as my R, what happens is I get a point that's about negative 3.24. As the x value, and about negative 2.35 as the y value. So what happened there was because my R was negative, it actually shot backwards along this trajectory. Does that make sense? So normally with angle pi over 5, it's shooting frontwards into the first quadrant. But since that R was negative, it shot back along that same directory, along that same direction in the opposite. So same line, opposite direction. If I drew this properly, it would be a perfectly straight line. Okay. And that also tells you that just for the sake of understanding this, if somebody put in a +4 and then 6 pi over 5, you can calculate this. Oops. And see that you get the exact same point that we got here. Okay. It's just, you can go 180-degree swing of what your angle is, and then go the opposite direction. That's basically the idea. Or pi rotation. So pi rotation with a negative R. Same thing. Any questions about that? That makes sense? Why we're doing what we're doing. Now, as far as like doing actual calculations, this should be fairly straightforward in terms of the process of calculating, I hope. We go 4, 6 pi over 5, just plug it into our calculator if all else fails. Okay. Obviously, if you know exact answers, you could, but you can always plug that in your calculator. And get the correct value. X is equal to R cosine theta. Y is equal to R times sine theta. Now, going the other way can get a little bit tricky because of this phenomenon, right? And so we're gonna have to pick an angle to use, basically. All right, does that make sense? So we're going to convert from rectangular to polar. And in our answers, we're going to use theta between negative pi over 2 and 3 pi over 2 and non-negative R values. We can't use negative R values. We're going to say that. Now you might ask, why did I use from negative pi over 2 to 3 pi over 2? I'll explain that later, but it has to do with the fact of what inverse tangent gives us. Does that make sense? Inverse tangent is going to give us an angle between negative pi over 2 and positive pi over 2. If you remember back to that section when we were dealing with the inverse tangent function on our calculator, it was in this. It always gave me an angle in either the first quadrant or the fourth quadrant. So inverse tangent gives you angles in here. And so we'll start at negative pi/2 and then go all the way around. And we'll all just use positive values for R. So let's talk about, or let's start with the rectangular coordinates, x comma y. Let's say I have 5, -2. And I want to convert those to polar coordinates of r comma theta. Well, I'm gonna have to do a little bit of work. I guess not that much work, but let me state it this way. Since 5, -2 is in quadrant 4, I am not going to adjust what the inverse tan gives me. Because inverse tan gives me quadrant 4 and 1, right? 1 and 4. So all I have to do to find my R is use that first equation. Square root x squared plus y squared. And then to find my theta, I have to do tan inverse y over x. In my case, I'm sorry, I forgot something that was obvious that I'll say though, even though it's obvious. I'm using the positive square root because I asking for non-negative r's, right? Using positive square root because I'm asking for non-negative r's. So in our case, positive square root of 5 squared plus -2 squared. And then tan inverse of -2 over 5. So the square root of 5 squared plus 2 squared is approximately equal to 5.39. Roughly. And the inverse tan, or the arctan, of -2 over 5. And again, I'm just typing these things in, is a -0.38. -0.38 radians. Now this should make sense. -0.38 is shooting you off into the 4th quadrant with a positive R. You're getting a point somewhere down here So yeah, 5, -2 makes sense. If you wanted to check this out, you could always reverse engineer and say, well, x is r times cosine theta, and typing in these, you should get something pretty close to 5. It's rounded, so it's not going to give you exactly 5, but. And if I do r times sine theta with typing in those, you should get something pretty close to -2. Rounded, so it won't be exactly -2, but close. Does that work? All right. So here's where it gets a little sticky or tricky or whatever. Let's say we want to find the polar coordinate of the rectangular point -5, +2. So if I want a non-negative r, I'm going to take the positive square root of x squared plus y squared. And if I want my angle theta, here's the only tough part. We have to realize that the theta that I want versus the theta that my calculator is going to give me when I put in inverse tan are going to be pi radians away from each other. 5, -2 is going to shoot down into the 4th quadrant. But the one we're dealing with now, -5, 2, actually shoots us into the 2nd quadrant. But it's on that same straight line. Okay. So what I'm going to do is I'm going to take this angle. My calculator only gives me angles from quadrant 4 and quadrant 1. And I'm going to add pi to it. With all that. So I'm going to write it down as what I just said. I'm going to take tangent inverse, and then I'm going to add pi. Write that all down. Positive square root of -5 squared plus +2 squared, comma, inverse tangent 2 over -5 plus pi. By the way, does everybody understand why putting -2 over +5 and then +2 over -5 give you the same thing when we take inverse tangent, right? Because they're the same fraction. -2 over +5 or +2 over -5 are the same fraction. So they're going to give you the same angle with inverse tangent, which in my case is going to give you an angle in the 4th quadrant. So if I wanted to shoot back in the 2nd quadrant, it's going to add pi to it. By the way, the other kind of method that sometimes people use is they'll just put the negative square root in front if it's in the 2nd or 3rd quadrant, instead of adding pi. So they allow negative r's, and then they use theta in between -pi/2 and +pi/2. and you get about 2.76 as your angle. Does that make sense? A little less than pi. And that's what you're gonna do every time. Let me write that down. If your point is in quadrant 1, or I should say, let me rephrase that, quadrants 1 or 4. Then let your angle be inverse tangent y over x. If the rectangular point is in quadrants 2 or 3, then let your angle be inverse tangent on your calculator of y over x plus pi. And if we want a non-negative r, we always take a positive square root. So that work? So that has to be the way it goes. I mean, it has to be that way in order to get correct angles with these parameters. And that's why we have these parameters. If you think about negative pi over 2, that's as far down here as we can go into the 4th quadrant. And then I can go up to pi over 2 into the 1st quadrant. And then if I add pi to that, at most I can get is 3 pi over 2. So that's why the angles usually are bounded by negative pi over 2 to 3 pi over 2. So either you just use the angle that's given to you in your calculator, or use the angle given to in your calculator plus pi. Is that right? So that's the big conversions of points. Now that you know how to do that, you can do, I think the first, like, at least the first portion of 8.3 and 8.4. Any questions about this? Easy stuff. All right, well, I'll see you all on Wednesday, and I'll be here at normal time on Wednesday because I don't have to travel through an airport terminal. So, all right, I'll see you then.